Well, I have here a little video that's going to describe what I call the Lorenz force, or commonly called the magnetic force, which is an interesting contrast to the electric force. Now, the electric force, very early in our study of electrostatics, we described how charged particles have a force exerted on them by an electric field. And that electric field would have been created by some other charged particles somewhere, but we're usually not concerned with those, just the field that they create. There's a fairly simple relationship that the force exerted is for a positive charge in the direction of the field and directly proportional to how strong the field is and how big the charge is that the force is exerted on. So, an interesting contrast is with the magnetic force, and this is sometimes written F sub B. B is our symbol for the magnetic field, that there's another quantity that's important. In addition to the field, and you can see in this equation, the force is directly proportional to how strong the field is, and also directly proportional to how big the charge is on which that force is exerted. But here's the other quantity. There's the velocity vector involved. And this shouldn't surprise you. When we learn how magnetic fields are created, we learn that we need moving charges to create a magnetic field. And so when those fields exert forces, they exert forces only on other moving charges. So we say that the magnetic force is QV cross B. This particular diagram here doesn't look much like a cross, but make sure we see that there's the cross product, because that's how we're going to figure out what the direction is. So the magnitude part of this is not too hard to figure out. Usually you're going to be asked separately what the magnitude is and what the direction is. So when you do the magnitude part, you just put each of the three quantities in, QBB, and then it would be the sine of the angle in between the velocity and the field directions. And then the direction part of it, you do with a right-hand rule, as you do with all cross products. So here's an example here of what that force would look like. Now we're trying to draw 3 dimensions on just a 2-dimensional screen, which is a little challenging. So what we have here is a positive test charge moving rightward. That's the red velocity vector. And it is in a field that it looks in this picture like it's diagonally up, but this is actually trying to show a B field that is going into your screen. And so when we cross those two, there's 2 ways we can do this. I like to imagine spinning that velocity vector, the rightward vector, kind of back away from me towards the magnetic field vector. And if I do that with my right-handed fingers, my thumb naturally points up, and that will give me the direction of the force. Important characteristic here is that that force will always be perpendicular to both the velocity and the magnetic field vector directions. Now there's 2 directions that can be perpendicular to both of those, and so that's why it's important that you do the right-hand rule so that you get the proper direction for a positive test charge. If you have a negative test charge, like an electron, a very common situation, then you have to remember either to use your left hand or to just reverse the answer that you get by doing the right-hand rule. So because of this perpendicularity, it's very interesting implications. And this is a review of some basic kinematics. If you have a force that is perpendicular to the motion, there's no way that that force can cause a speeding up or slowing down of the object. But instead, that force will cause a change in direction. So what happens in this case is if we have the velocity vector that is completely perpendicular to the B field direction, I'm going to put little vector symbols on these, then the result is circular motion. I'm going to do something more with that in just a moment. And if your velocity vector is only partly perpendicular to the B field direction, then we cannot change the motion in the direction of the B field. So we will create a helical path where the path is actually still in the direction of the B field, but also circles around. So we make this nice little corkscrew shape or a helical shape, and there's a picture of that down here. So Let's look at this circular motion, because there's a real common thing. There's a lot of devices out there that actually exploit this characteristic. One is known as a mass spectrometer, and it's actually a big machine for determining the mass of small particles. Like if you have an unknown material, sometimes you can figure out what it is just by putting it in the machine and see how it circulates inside of a magnetic field, and that can tell you what the mass of the object must be, which helps you pinpoint what kind of material it could be. So I'm going to show you how we derive the equation for the circular motion of one of these. So here on the screen you see an upward moving positive charge. That's the red vector. And it enters a magnetic field that is out of the page. And I've purposely made those completely perpendicular to each other, so we're only going to get a circle and not a helical path. And we might be asked, what kind of radius would this circle have? Or what kind of mass would cause a certain radius? And let me show you how simple it is to derive the relationships between all those. It actually starts with a very familiar F equals ma. So if we only have one force causing the circular motion, that is our net force. And in this situation, that net force is the magnetic force, F sub b. And what kind of acceleration does this cause? Remember, it's not a speeding up or slowing down. It is a centripetal acceleration that just changes the direction of the motion and causes the circle. So now I'm going to substitute in Q, V, B, and I'm going to leave out the sign of 90 because it's just 1. And over on this side, I have the mass of that charged particle, and then our expression for centripetal acceleration, which is V squared over R. I'm going to label on here, I'm using capital R for the radius of the circle that's made. And so what happens very nicely here is we have a V on this side that will cancel out one of the V's on this side, and then just with a little bit more algebra, here's the relationship QBR, let me write it this way, QBR equals MV. I'm going to stop there because depending on the problem that you have, you might be asked for any one of those 5 quantities. Like I said, if we know that we've created a certain magnetic field and we know what the charge is on our particle, then determining the size of the circle can get us the mass. And then, of course, we also have to know the velocity. So you just have different variations on that particular kind of problem depending on the situation. So neat little connection back with mechanics here. And I think that should be an equation you should be able to derive without too much trouble. So that's a good look at the Lorenz force and the circular motion that can result from it. And I think I'll let you work out some more of the details on your own. That's it for now.